Hello everyone. On the board it seems like we have a typical algebra problem. But this is why we're here today. We are going to be exploring a method where we prove equations or similarly solve system of equations using geometry. And also we'll be going through typical formulas or identities that will occur in IB program. Okay, so the problem is, suppose we have angles alpha, beta, and gamma, and they are all strictly greater than 0. And we also have alpha plus beta plus gamma equals pi radians. Okay, so radians, and if you're in IB, you'll be using radians a lot. So just saying here, pi radians is 180 degrees. So you should be comfortable of converting radians into degrees and degrees into radians. Now, given these information, we want to prove this following equation. Sine 2 alpha plus sine 2 beta plus sine 2 gamma equals 4 times sine alpha times sine beta times sine gamma. Okay, so it seems like a typical algebra problem, right? So the first thing that you might want to do is to resolve this compound angle difficulty right here, right? So this is also another common IB identity that you'll learn in like IB1. Alright, so it's called the double angle formula. And what this is sine 2 alpha. Sine 2 alpha equals 2 sine alpha times cosine alpha. Okay, so this is called the double angle identity. I'll write it here. Yeah, okay, identity. You want to remove the compound angle right here. You want to remove the 2 alpha. And if you do that to each of the terms, sine 2 alpha, sine 2 beta, and sine 2 gamma, you'll realize that you have created a cosine term, right? And this is not what we really want because we do not see a cosine right here. So this will get pretty complicated. And also, you can prove this identity by using angle addition formula like sine alpha plus beta in brackets. And this is also another identity you'll learn in IB1. Okay, so this will obviously result into something really complicated. However, we may notice that we have a lot of angles. And whenever we hear about angles, we think of geometry. Okay, so pi radians, 108 degrees. What do we think of? We think of triangles, right? Because the angles of the triangle add up to 180 degrees. We may also think of circles because a circle is 360 degrees. 180 degrees and 360 degrees are really closely related. So here we have a circle. And then watch, I'm going to draw a triangle. Okay, maybe not the line I was expecting. Okay, okay. Okay, I'll also be labeling the point, so let the center of the circle be O. And we're gonna let the vertices be A, B, and C. Also, this is a unit circle. Circle O is a unit circle. So therefore, we let the radius be 1. Now, the reason why we do this, well, this is just simpler. We can let the radius be anything, and after we get an equation, we multiply by some constant. It'll be the same, but 1 is a really easy number to work with here. Alright, so we have alpha plus beta plus gamma equals pi radians. Now, if we double this equation, we get 2 alpha plus 2 beta plus 2 gamma equals 2 pi radians. You know what else is 2 pi radians? Well, it is this angle right here, this big angle right here. This entire circle is 2 pi radians. So we can do this. I'll Okay, so we have this. Now this is a perfectly valid construction right here. These add up to 360 degrees. Okay, so now we have gotten our geometry. We represented this equation using geometry. Now we just want to prove that this is equal. Now how do we do that? There are like a few ways. For example, if you have a line segment and you find two different ways to calculate that line segment, right? Then these two expressions you have used to represent that the length of the line segment, well, they must be equal. But here, one thing we might think of is calculating the area of the triangle. So we might find two different ways to calculate the area of triangle ABC. And it is clear that we have two ways, first of all. So first we can calculate the area of this triangle plus the area of this triangle plus the area of this triangle. This will give us the area of triangle ABC. And another way we can do this is just calculate the area of triangle ABC directly. Yeah, we have these two expressions, and because they both represent the area of triangle ABC, they must be equal, therefore. Now, notice that we have isosceles triangles right here. So OAB, OBC, OCA, they are isosceles, right? So therefore we can receive information of all their angles. Now because this is isosceles, therefore angle OAB equals angle OBA. And what will that equal? I'll use radians here. Normally I write 90 degrees minus alpha, but because the problem states radians, it is a good idea, good habit to stay consistent between degrees and radians. So this will be pi over 2. 90 degrees is pi over 2. So pi over 2 minus alpha. This is the same thing right here. Oh, okay. Pi over 2 minus alpha. This will be pi over 2 minus beta. Okay, now we have labeled our angles. Also, good habit of doing these diagrams. So if you find information of some angles or side length, it is usually a good idea to label it on your diagram so you don't forget later or confuse yourself. Okay, so now we have information about all the angles. Now, what's one way of finding the area of triangle ABC? Well, we're going to use this notation to denote the area. So this means that this bracket around is the area of triangle ABC. This is a standard notation. You'll find it in books like AOPS. Okay, so the area of triangle ABC equals the area of triangle, call it OAB, plus the area of triangle OBC. Okay, here let's get into some prerequisite knowledge right here. So we have this nice triangle. Okay, we have this triangle. Okay, so suppose this is alpha, this will be angle beta, this is gamma. So let this be have side length A, all right? This will be side length C. This will have this side length will have length B. So to calculate the area of this triangle, you also get into this formula probably in IB. Okay, so the area of this triangle. So suppose we're using angle alpha, for example. It will be half sine alpha times, so this angle alpha is in between side lengths B and C. So it will be times B, capitals B, and times C. Now similarly, if we want to do it with this angle, well, it will be half sine beta times A times this side length C. And Same thing here for gamma. Okay, so given this, now we find the area of triangle OAB. And by doing so, it will be half times 1 times 1 times sine 2 alpha. So this will give us sine half times sine 2 alpha. We will be doing the same for triangle OBC. Okay, so this will be the area of triangle ABC. So this is one way we can find the area of triangle ABC. Another way we can do this is, instead of adding the area of these three triangles, we can apply the same formula right here, except we'll be using the angle of triangle ABC itself. For example, this angle right here, this angle right here, and this angle right here. But the only information we're missing here is the side length of triangle ABC. So how do we find that? Now I'm gonna draw an altitude with a different color. Okay, so you know what, let's call the foot of this altitude, this is an altitude right here. Let's call this point D. Now, if you want to show that BD equals CD, well, I mean, we use congruent triangles right here. And this is not a very important scale in geometry. So, because OB equals OC, and OD equals OD, and we also have these two angles equal to each other, therefore, the triangle ODB and triangle ODC are congruent. So this means that DB equals DC. Okay, another important law you'll learn, I learned it in pre-IB, so like in grade 9, is the law of sines. And basically what this formula states is that, so sine alpha over the opposite side, the side is opposite to, this will be capitals A, equals sine beta over B, because B, capitals B is opposite to this beta angle, equals sine gamma over C. So this right here is called the law of sines. Law of sines. And we will be using that right here. Okay. So how do we use law of sines right here? So we have this OB. So 1 over sine 90 degrees. Actually, no, sine pi over 2. Equals, so we want to receive information about the side length of triangle ABC, so therefore we're finding BD. So BD is, now because these two triangles are congruent, therefore angle DOB equals angle DOC equals beta. So therefore this equals BD over sine beta. Now here, because sine pi over 2 is 1, therefore, after multiplying both sides of this equation by sine beta, you will get BD equals sine beta. So let's go mark that right here. Alright, so we have sine beta. This is the side length. So if you also draw altitudes on this triangle, OAB, and draw an altitude right here on triangle OAC, you'll also receive information about the side length of AB and AC, and you'll work out, and then this will equal 2 sine alpha. This right here will equal 2 sine gamma. Now we have enough information to calculate the area of triangle ABC. So here's another way to, so this is the first way to do this. Now the second way to calculate the area of triangle ABC is using the exact same formula up here, except we will be doing it for, let's say, on angle BAC. It works for like any angle right here. You can do on ABC, you can do on ACB, but let's just do it on angle BAC. So this will equal half sine. So if we add these two angles together, you get pi minus alpha minus gamma. Okay, and then this angle is in between two side lengths. These side lengths have length 2 sine alpha and 2 sine gamma. Okay, now recall this equation right here. So this given condition. So pi minus alpha minus beta. If we move alpha and beta over, you get gamma. So therefore, this equals half times sine gamma times 2 sine alpha. Wait. Okay, wait, hold on. Sorry, this is supposed to be pi minus alpha minus gamma. Okay, so therefore, by moving alpha and gamma over, you get beta equals pi minus alpha minus gamma. Okay, so you have half sine beta times 2 sine alpha times 2 sine gamma. And this equals 2 sine alpha times sine beta times sine gamma. Because both of these expressions represent the area of triangle ABC, therefore they must be equal. Okay, let's go write that down. Okay. Equals 2 sine. And now by just multiplying both sides of this equation by 2, you get the desired result. So I'll just go do that. Okay, and we are done. So in this video, we basically explored a method of how we can use geometry to prove equations, algebraic equations, and also potentially solve complex system of equations. So whenever you see an equation or complex system equation that's not really easy to deal with, always remember that one good way to solve these equations or system is to represent these equations using a geometry diagram. And especially if you see angles right here, like in this case. So we have pi radians, right, 180 degrees. This hints us a lot towards circles and triangles. Now usually these geometry diagrams, like very often there'll be triangles or maybe triangles inscribed into circles. So just be on the lookout of this strategy. Thank you very much for watching.